Hello dear colleagues, and another welcome to your channel. In this video we're going to continue our tutorial about steel structures and continue our lesson about steel characteristics. Okay, in this video I'm going to start with this amazing uh, property of steel that I'm going to name it radius of gyration. Let me write that. Sorry. Uh, Radius of gyration. This property is important when we want to design some compression element or elements that are in compression load. It's really important, and the relation of radius of gyration is this. We have here R2 times A is equal to I. This is the relation, and we have here R is equal to radical I divided by A. R is radius of gyration. Let me write the definition of radius of gyration. We have here radius of gyration is distance between neutral axis. Radius of gyration is distance between neutral axis of section to imaginary point where at that point we could concentrate all of section. That was the best definition that I could tell you about radius of gyration. I want to repeat the definition and once again read that for you. Radius of gyration is distance between neutral axis of section to imaginary point, where at that point we could concentrate all of section, and I wrote the equation for you, but be careful that radius of gyration mostly applies for compression element. I want to solve a problem for you now. Let me close this topic. Okay, for example, we have a rectangular here, that has two axes. One dimension is T and another dimension is B. You see, we want to calculate the radius of gyration about a strong axis to radius of gyration of weak axis. We want to find our strong axis divided by radius of gyration of weak axis. So let me solve that. We know the equation of radius of gyration, which is r is equal to moment of inertia divided by section. And we have here moment of inertia of strong axis, which is equal to t times b to the power of 3, or cubic b divided by 12. And we have here the moment of inertia of weak axis, which is equal to b times cubic t divided by 12. You see, and the section of rectangle about two axes is equal. We have here a1 is equal to a2, or section of a strong axis is equal to section of weak axis. So we can write now the equation. So here r strong axis divided by r of weak axis, we could remove sections, and we have here radical I1 divided by I2, which is equal to radical t times cubic b divided by 12 divided by b times t to the power of 3 divided by 12, which is equal to b divided by t. And this is our answer. We just get familiar with radius of gyration, and we have already solved a problem for that. Let's continue, everybody. And another property of steel that I'm going to name it torsional constant, and we're going to show that with J. Let's continue. Our another property is torsional. Torsional constant, which we're going to show that with J. The unit of J is millimeter to the power of 4. The torsional constants of a section show us how much this section is strong about torsional moment. It's about moment, torsional moment. And another property that I want to tell you is the warping constant. Let me write that. Is warping constant, that we show that with CW. The unit of warping constant is millimeter to the power of 6. You see, the process of calculating CW is far difficult from a torsional constant. And because of this, we're gonna memorize the relation of CW for every section, channel, I-beam, you see. For example, for a I section with a symmetry axis, we have CW. Let me write that. I always couldn't draw a simple thing like that. Really. Okay, no problem, everybody. You suppose that this is straight and we have one symmetry axis. And this is our symmetry axis about y axis. And the dimension of section is d, the height of the section, and we have here CW is equal to moment of inertia about y-axis times the height of the section to the power of 2 divided by 4, and we have some more relation for that, but I don't want to spend time for that. You can go to reference books and extract them. Okay, let's continue, everybody. So let me continue and see what we have next. Okay. Okay, now I want to introduce you with another content of a steel that which its name is a local buckling. You see, suppose that we have an I section when it wants to have a local buckling, the shape of a section would be like this, and we have wrapping in both flange and web of section. We have something like this. How could we define which section is with sorry, let me tell that like this. How can we find a section would have a local buckling or not? You see? Okay, let me continue. How can we define a section would have a local buckling or not? Okay, we illustrate that, we define that with a content that we call it slenderness factor. Let me write our topic for you. Our topic is about local, let me write that again, is about local buckling, you see, and we define the local buckling with a factor that we call it slenderness, a slender slenderness, we name it slenderness factor. You see, uh, okay. For example, the slenderness factor has some relation and some rule that I will write that for you. For example, uh, the half of the half width of our section, for example, is B, and the thickness of our section is T. Okay, uh, how can we calculate the slenderness factor for this uh, topic? Okay, uh, let me write that for you. Uh, the slenderness factor equation for this section, IPE section, is being calculated like this. B divided by T have to be less than 0.76 radical E divided by yield stress. If we have this rule, our uh, column, for example, I'm going to write that element. Our element is not slender. Okay, and we have, if we have uh, B divided by T greater than 0.56 radical E divided by yield stress, our element is slender, you know? Okay, but the thing that I'm gonna remind you is that uh, be careful that every single section has its own relation for local buckling. You see, you have to know that, everybody. For example, I write the relation for I section, and we have uh, another relation for tube section, another section for another rule for box section, and etc. You see? Okay. Let me continue for you. Let me tell you that if a section is not a slender, we call it a compact section, you know. But if a section is not is a slender, we call it non-compact section. Okay. Uh, Let me continue our topic for you. And go on. Uh, okay, I don't want to solve a problem for this topic because uh, it's a bit long and has uh, actually hard relations. Okay, I want to tell you that what now our topic is rules of sorry method. Methods of uh, steel structure method of steel structures uh, design. You know, okay, we have some important. We have three important ways to analyzing of for analyzing of steel structures. You know, everybody. The first one is the first design. Okay, let me correct that. It's design and analyze. For design and analyze. Okay, the first uh, method for design and for analyze and design the steel structure is direct analysis method. Let me write that. Is direct analysis is direct analysis method, and this second one is effective length method. And the third one is first order analysis method. These are three most important ways to analyze and designing of steel structures. Okay, let me write that. First order analysis method. Okay, every single method has definition and rule and its own rules, you know. But I don't see that to be so important for you to explain completely. But I just in this session, I just want to uh, just introduce that for you. You know, let me continue and continue again. And now I want to open. Uh, Now I want to open another important topic, which is design of tensile sections. Okay, let me continue. Uh, Let me write our topic. Our topic is about design of tensile elements. Okay, uh, tensile elements have uh, uh, have are practical in our section, for example, in braces section or beam section, and for example, in the for example, tensile reinforcement in foundation and etc. You know, for example, let me draw a frame for you. suppose that we have a frame. This is our frame. And this is the section. And this is the gusset plate. Here we have here a tensile element of brace, and now I want to draw some detail for this. One detail for this area and one detail for this area. This is detail 2 and I will name it detail 1. In the detail 1 we have a gusset plate here, and we have a element here. And this is the section, and we suppose that our element is connected to gusset plate with 3, for example, joint. Okay, we have here the tensile force that we call it T. You see, and we learned that in this circumstance we have tensile load. Okay, let me draw a detail for second one. Sorry, for the second circumstance we have here, this is our section cut. And for the detail 2, this is detail 1 and this is detail 2. 2 tensile force. These are tensile force. And these are hole for connecting. Okay, let's continue, everybody. Okay, this was one case for tensile forces. Okay, we have another case. For example, we have a tensile element, for example, which is a plate for us. Okay, and which is under 2 tensile force, you see, and has 3 holes. There is not any, be careful that there is not any bolt here. And the way for calculating tensile force is, for example, I want to make a section here, and for example, I want to make a section cut here and name that A. Let me draw what is happening in this section. In this section, there is not any hole and there is just pure tensile force. And in this section A, we have axial force in A section. We call it NA. And let me write the uh, equilibrium equation, which is sigma of Fx is equal to 0. This is the equilibrium equation that we have. The axial force of A is equal to T. Now I want to make a section chord here and name that B. You see, in the B section, we have a pure element which have two loads, T and we have here axial load of B, and this is our hole. You see, when we write an equilibrium equation, we have sigma of Fx is equal to 0, so we have NB is equal to T again. You see, and I want to make a section chord here, C, and we have here the element for C, and this we have here T, and we have here uh, axial load for C. We have here sigma Fx is equal to 0, then uh, axial load for 3 is T. Okay, and we have here two hole, you know. Okay, let me continue. You know that if you wonder now why we have uh, n of A, n of B, and n of C is equal to 0 is equal to T, whereas we have three hole here, you see, because of these hole there is not any connection. We have here just hole. Due to this hole, because of this hole, we have pure load in every section. The value of tension, the value of tensile force will not be decreased. You know, let me continue and show a case of connection. Okay, for example, for example, we have a plate here. Uh, we have we have a plate here. This is our section chord. We have here a plate, you know, and there is a tensile element here, and we have which is connected to this plate with 3 volt. Be careful that here we have connection. At that case, at previous case, we didn't have any connection. Okay, and this here we have tensile force T, and there is another T here, and these are the section chord that I want to uh, address. There is a section chord here A, there is another section chord here B, there and another section chord here C. Okay, let me uh, illustrate that for you. Here we have uh, section A, this is tensile force, and we have here NA, okay, and this is T, and we have here NA. We have axial force of NA is equal to T, but when we want to uh, have another section, this is my T, and here we have a connection, and here we have N of B, and there is here a force, which is 1 divided by 3 of T. This force is this force is endured by a bolt, you know, and we have here we have a force for C, and here we have tensile force uh, T, and here we have 2 bolts, which every single of them endure 1.1 divided by 3 of tensile force. Here we have 33% of T, and here we have 33% of T, and here we have, let me continue, I forget to write that, NB is equal to T minus 1 divided by 3 of T, which is equal to 2 divided by 3 of T. For example, the value of T will be decreased about 0.33% because of that bolt, and here we have NC, which is equal to T minus 2 divided by 3 of T, because we have 2 bolts here, and the answer is 1 divided by 3 of T. The value of T will be decreased about 0.66%. Because of 2 bolt, we decrease the value of T about 0.66, Okay, that was the definition for tensile force when we have connection and when we don't have a connection. You see? Okay, now I want to introduce you the content for gross section, and pure section. Okay, let me continue. Let me continue for that. For example, at first, I want to introduce the cross section. Suppose that we have an element here which is under two tensile force. Let me show the mass of that. This is a element which is under two tensile force, and the thickness of section is T and the width of section is B. So we have the gross section here. The thickness is T and the width is B. So the gross section that we show that with AG is equal to B times T. You see? Uh, so we have another content uh, that shows the net section. Here we have gross section and now we have net section. Let me write that. Now we have net section. Okay, we have that section. Now we added a hole for that. This is the same section with added just a hole. Suppose that this is, sorry, this is our B I. This is our B and this is our hole, and this is the rest of section. This is our hole. And we have here AN equal to B minus the diameter of hole times T, and this is our B and this is the diameter of our hole, which is D. Now we have AN is equal to B minus D times T. Let me continue. That was the definition for cross section and next section, which is really, really practical uh, when we want to solve problems about tensile sections, tensile elements. Okay, another thing that I want to address for you is that uh, for connection of tensile and other cases of connections. For example, when we want to have a connection with M16 bolt, uh, what would be the circumstance for hole? For example, let me write that we have M16 bolt. So the value of hole would be 2 millimeter greater than the value of bolt. We have here the value of D to be 18 millimeter because of executions cases. For example, or we have M18 bolt, the value of the must be 20 millimeter. Be careful that every single circumstance, every single connection, the value of the value for hole should be at least 2 millimeter greater than the value of bolt. Okay, that was another content that I want to address that for you. Let me continue, everybody, uh, and have our topic about tensile elements. Okay, let me continue and find. Okay, now I want to address the effective of uh, holds in connection. Okay, so the effect of our topic, I missed my pen. The effective of the effect of staggered the effect of a staggered hole in nets area. Uh, let me in net area. Okay, suppose that we have a plate and we want to bolt it or have a connection of it. This is our plate. I apologize. I want to make a section code. This is our plate and these are our section code, and we have here tensile force T and have here tensile force T, and the width for our section is B. And we have here two staggered hole for our section. This name is B and C, and the distance between two staggered hole R is S, and the vertical distance between these two joints is G, you know. So let me repeat that. The horizontal distance between these two joints is S, and the vertical distance is G. Okay. uh, how can we consider the effect of staggered holds in calculating of net section? You know, for doing this, we have to make some section cut, in some direction. You see, let me continue. For example, the first, let me change my marker. We have to make some direction. You see, the first direction is vertical and straight direction, which is A, B, and E. This is the first direction. In the uh, in the A, B, E direction, we have the net area and we call it AN1 is equal to B, as I told you before, B minus the uh, diameter of hole, which is D, times T, the thickness of section. You know, and in basic codes, you know, uh, if we consider in some section a staggered direction, we add a equation for that section cut. Let me tell you what is that. For example, I want you another. I want to make another direction. You see, which is A B C D. We have here A B E direction, and now I want to add A B C D direction, which is actually a staggered direction. And the name of this point, let me show you the direction. This is A and B and C, and here we have D, A, B, C, D direction. Okay, we have here for this direction AN2, which is equal to, that we have two holes, B and C. B minus 2D, plus S to the power of 2 divided by 4 times G times D. You have to memorize this formula, S2 divided by 4G, in every staggered direction, Uh, let me write that for you. We add, let me write that for you. Uh, for, let me write that. For every, staggered direction, we add, we add S to the power of 2 divided by 4 times G to our calculation, You have to memorize that. We use this formula in every equation. Okay, but another important thing, which is really important in calculating net area, is that, for example, you have four, five, six direction. For calculating net area, we chose the minimum value of every direction. Uh, Let me close this thing. Uh, we have here the minimum of an is equal to minimum in an1 and an2 and etc. you know and if we have a staggered direction, the value of an is equal to b minus nd. For example, you have four or five staggered direction. Here we chose n is equal to b minus nd. D is the value for diameter plus sigma of s to the power of 2 divided by 4g, times t. This is the value of a minimum of an when we have a uh, staggered direction. Let me continue what we did have in this session. Review that in this session, everybody. Let me find that. At first, the first of our session, we introduced the radius of gyration for a steel, that had this equation, and we solved a problem for that, and we uh, addressed that. The radius of gyration is uh, practical for compression elements. Okay, let me and then we introduced torsional constant, which we show that with J, and wrapping constant. And I told you that the wrapping constant, the process of calculating CW is a bit hard, and you have to memorize the relation for that. And as you can see, I wrote I've written a equation for I beam with a symmetry axis. Okay, and then again we enter to subject of local buckling. And I told you what is local buckling, and what would be the reaction of us when we want to know what uh, when we want to know if local buckling is probable for one section or not. And I told you that we're gonna know this content with a slenderness factor, which our slenderness factor as a relation. Okay, and in continue, I introduced you some method for analyze and designing of steel structures, direct, effective lengths, and first order analysis. Okay, and in continue, we enter to the topic for tensile, designing of tensile forces, tensile elements. I made the example and I told you that we have tensile force in braces, and I told you the difference between a tensor element when we have a connection or not. For example, in this example, we have connection. And in continue, we introduce the growth section and next section and the calculation related to them. And then we enter to effect of staggered hold in calculating net area. I've told you the calculation, and in continue for the next session, everybody, I will solve some problem for calculating net area. This is for me calculating of tensor elements and design of tensor elements is really attractive for me, and I will solve many problems for you. Okay, now I hope that you all not be tired, and I hope that you all enjoy my topic, and I hope that it will be so. And if you like the video, everybody, I want you all to subscribe my channel to motivate me to create more videos for you. Thank you, everybody. Thank you very much.